Hello, my name is Nate Youmans, and this presentation is all about the research work I've been doing over the summer with the OREU program at Texas A&M. Before I get too much into it, I want to thank the sponsors, the OREU program, and also this work is sponsored by the U.S. Department of Energy, the National Nuclear Security Administration. I also want to thank my collaborators, Dr. Dimitris Lududas, and then my mentors, Dr. Joe Joy and Dr. Manish Vasoria, and the rest of the Smarten team there at Texas A&M. So let's get into what I was doing over the summer and the project analyzing metastructured shape memory alloys. So before we get too into what I've been actually doing, what are shape memory alloys and what are metastructures? So shape memory alloys are metals that can change their material properties as a response to different temperatures and stresses. So most materials, like aluminum or something, it's got one set of material properties and that's kind of it. SMAs can actually transform between two different phases, between the martensite and the austenite phase, and have different properties for each. And you can control that transformation by adjusting the temperature of the material or putting stresses on the material. So typically, if you increase the load on a SMA, the temperature that you need to transform it goes up. But that can lead to a lot of different interesting responses whenever you're dealing with making structures out of SMAs. Moving on to metastructures. Metastructures is a pretty broad term, but it refers to structures that yield unique material properties based on the structure they're made in, not necessarily the material itself. So they typically involve repeating patterns and microscopic micro structures. Specifically in this project, we're also going to be looking at adaptive metastructures, where that unique material property that makes it a metastructure is the fact that it reacts to an external stimulus. So for example, if you had a material that got harder the more load you put on it, that would be an adaptive structure, right? It's reacting kind of uniquely to that external stimulus. And the way that interacts with shape memory alloys also makes a lot of sense, that as it transforms, it changes its properties adaptively to its environment. The specific metastructure we'll be looking at in this project is an infinite volume of shape memory alloy with a pattern of spherical voids. So here you can see a sample of it where you've got the cube of shape memory alloy and then these spherical voids inside of it. And this is three-dimensional, so you can imagine this going in all three dimensions, not just the two on the slide. And what we want to analyze is the actual response and the effect of the voids on that metastructure. Because it's a shape memory alloy, it's going to create these different stress concentrations, and it's going to transform in non-uniform ways, because some areas are going to have higher stress than others. And we want to analyze that response and see how the voids affect both the transformation and the elastic properties of the entire solid. Now, normally what we would do to solve this kind of thing, and ideally we would just create an analytical solution where we solve some differential equations and we can just solve that for any time, any stress, we can just calculate what the response is going to be for a solid. And unfortunately, an analytical solution doesn't exist for this problem. So we have to use a numerical solution. We have to use finite element method, specifically abacus, to find a solution. And unfortunately, finding a numerical solution for an infinite problem is a little bit challenging. But luckily, there's a workaround we can use to actually get to it. So in summary, what we want to analyze is the shape memory alloy response to the stress concentrations made by the voids in this metastructure. So because of all these holes, there's going to be some stress concentrations going on around them. And what we want to analyze is the SMA response to those concentrations and effectively see if we can reduce the stress concentration because of the SMA transformation, making an adaptive response. So the way we actually do that and simulate this infinite volume without actually doing that, because it's kind of impossible, is we just take one unit cell. So this is actually what the model looks like in abacus. You've got one cube with one spherical void in it, and it's got the loads on it like you'd expect, but it's also got periodic boundary conditions. And basically what these do is these essentially make the model think that it's got an infinite number of neighbors next to it in all directions. So what it actually does is it creates constraints between the opposing faces, so that if, for example, if it deforms and pushes out to the right,
it also feels that push from the left, effectively making it think it's in that infinite volume. So we impose those, and then we also do a thermal cycle. So we take the entire model and uniformly cycle it thermally throughout the entire shape memory alloy transformation. Because again, the SMAs are, their transformation is a function of both temperature and stress. And so we cycle it through the full temperatures to make sure to get the full transformation all the time. Now, even though there's no analytical solution for the problem in this project, we can still compare it to similar problems that do have analytical solutions. So specifically, Kirch's solution is a similar problem to mine, the main difference being that it's in 2 dimensions rather than 3. But this graphic shows us what the internal stresses should be as a ratio of the applied load. So if we look right here in this box, this suggests that right above the void, the left-right stress should be exactly negative of whatever is applied. And if we look over here at my solution, with a 200 megapascal load applied, then we see that the load here is about minus 200. So it does line up, and it does suggest that we are doing kind of the right thing. Even though it's not the solution to my exact problem, it does still suggest that we are doing kind of the right thing and actually looking in the right place. Here's the actual analysis of the stress throughout the transformation. So here you can see the Martensite volume fraction on the left. This is basically tracking the progress of the transformation, and this is the stress. And you can see the spherical void cut into the blocks there. The thing to keep in mind throughout this is that the SMA's transformation is a function of both temperature and stress. So the high stress regions are the first ones to transform. So if we start here, this is just with the loading, and so this is kind of the response. These are the high stress regions. And as we go through this, you'll see there, the first regions to transform were the ones with the highest stress. And while they're transforming, the stress actually decreases. That bright blue spot is gone from the stress. It's actually redistributing the stress. Because as the SMA is transforming, the molecules are kind of moving around, and it becomes a softer material, kind of blunting and spreading out the applied load, the applied internal loads on it. So that's reducing the stress, but you'll notice right here, once it finishes transforming, this red section is finished transforming, it stops redistributing the load because it's no longer transforming. And we see that the stress is actually increasing all over again right here. And in fact, it actually increases the entire stress of the entire part. Once it's fully transformed, the stress is much higher than it was before, and that's because of all the internal stresses and strains that the SMA applies. So the same stresses that reduce the load in the beginning, they're still present at the end, but they're no longer really doing anything unique. They're just kind of increasing the stress of the entire part. So the key takeaways here are that the stress is reduced, but only during the transformation. When we have those light blues and greens on the left, that's whenever it's actually reducing the stress. But once it's finished, the stress is actually increased throughout the entire model. So in summary, we can see that the shape memory alloy does reduce the concentrated stress around the metastructure. It is an adaptive metastructure where the SMA does transform and reduce the stress at the concentrated points. But once it finishes transforming, then the stress is actually increased on net throughout the entire metastructure. We also saw that the stress response is comparable to a thin plate through the analytical solution that Kirch has. And we also found that as you increase the volume fraction, you increase the transformation temperature, effectively making the transformation happen sooner. And that makes sense because as you cut away more material, you kind of leave a weaker part, which leads to higher stresses, which leads to that section transforming sooner. Next steps that could be taken in this project could include biaxial loads or compression loads. I only looked at tension loads in one direction just for simplicity, but I'm sure there's some interesting results that you could find dealing with compression or shear loads. Other things we could look into were large volume fraction problems. So this is an example of a really large volume fraction. In fact, the radius of the void actually extends past the dimensions of the cube. Whenever I tried this a little bit, I ran into some divergence issues where Abacus couldn't solve this specific problem, so I'm not really sure what's going on, but that is something you could look into. Also, we can look into different regions of SMA. So a problem like this with different types of SMA and run some kind of optimization to reduce the stress even further, even more adaptively. Thank you.